kind of think that if you're in the asteroid belt, which is where a bunch of asteroids are hanging out, you have to be careful, like dodging asteroids, but there's a lot of space between asteroids, so that's kind of a misconception. Okay, so what's after the asteroid belt? Jupiter. Very good. How about the next planet? Saturn. Yep. So Jupiter and Saturn, in most images, they look kind of orangish like that, and they are. Okay. And the next two planets look kind of bluish, and they are. So they kind of go together. So if you're like me, sometimes you get these next two mixed up. So what comes after Saturn? Uranus, yes. Very good. And the last one? Neptune. And before I move on, do you see where Uranus, Uranus looks like it has some rings? Can you kind of see these rings around Uranus right here? Kind of these wispy sort of rings. Okay, so Uranus actually all, Jupiter has rings, or Saturn has rings, Uranus and Neptune, they all have rings. The thing about Uranus is actually it's laying down on its side. Does it look like it's kind of laying down on its side? I'll take purple here and kind of draw through. You remember how the Earth rotates on its axis? Okay, the axis that Uranus rotates on is basically kind of lies sideways. Very good. All right, so now you may or may not get this. I'll just go ahead and, so I don't try to coax it from you. But this, they look like asteroids, don't they? They look like asteroids. But it's very cold out here. Okay, you figure very cold, away from the sun. So they're not really necessarily rocky stuff as much as they have rock. They're made of rock and ice. Rock plus ice is equal to a comet. I know we're used to, oh, that's a comet in the sky. Come look at the comet. But only like we look at comets because they're exciting as they get close to the sun because they start to like evaporate a little bit. Most comets are just out here minding their own business. Okay? And actually there's a couple regions out there they hang out in. So very good. So this slide kind of says basically what we said. All of this stuff, all of these 4 planets you told me about, the asteroid belt, the other 4 planets, okay, the comets, they are all gravitationally associated with our sun. And for purposes of lecture, I've made this the sun this semester. So this is the sun. Okay, so we talked about the force of gravity. Basically, it's an attraction between 2 objects. And in this case, it's each of the objects and the sun. Okay, gravity. Okay, so from the sun moving outward, we have Mercury. You said that was the closest planet. Mercury actually has no moons. The first 4 planets are all rocky. The first 4 planets are all rocky. And I'll even put up the word here that I might use in my lecture notes. Not only are they rocky or whatever, but sometimes we call that terrestrial. Terrestrial. These first 4 planets are terrestrial, they're rocky. So Mercury, no moon. Venus, no moon. Earth, one honkin' beautiful moon. Mars has 2 moons, okay? And they are Mars's moons. Oh my gosh, they look like potatoes. They really do. They don't look like our moon. All right. So after that, we have the asteroid belt. And one of the things about the asteroid belt is it's thought that we're going to talk about how our planets formed. And it's thought that the big old Jupiter on the other side of the asteroid belt basically kind of screwed up those little pieces joining together to make something bigger. The gravity of Jupiter. You may know that Pluto is no more, but actually Pluto is classified as a dwarf planet. So dwarf planet is equal to Pluto. Okay, we have a handful of dwarf planets right now, probably getting more dwarf planets as we speak. But another dwarf planet actually is one of those asteroids, a large asteroid, the largest asteroid that is between Mars and Jupiter in the asteroid belt, Ceres. And Ceres has been visited by, I want to say, I get my spacecraft mixed up. I think it's Dawn, D-A-W-N. Spacecraft from NASA is at Ceres right now, finding some cool things. So, all right. Then we get to the big planets. Sometimes we call these gas giants, okay? Jupiter is actually the largest of the 4 gas giants. Now, I'll go ahead and put all of these up here, these 4. Okay, so these 4 are the gas giants. Sometimes we call them, so begin with Jupiter to Neptune. Sometimes we call them Jovian. Jovian. The word jovial means like happy. Maybe these are like happy planets. Okay, so these are the gas giants. The thing about the terrestrial planets is you could stand on any of those, okay? You know, Mercury, Venus, Earth, Mars. You could definitely stand on them. Anybody seen The Martian yet? Good. It's a good movie. But the thing about these is the surface of it is actually, you can't stand on it. So Jupiter has lots of moons, 67 moons by count that I could find. Saturn has 62 moons, Uranus has 27 moons, and Neptune has 13 moons. Okay, so they definitely have the whole moon thing going. We talked about the colors, kind of Jupiter and Saturn go together, and Uranus and Neptune go together. They're blue. We talked about Uranus is tilted. It's definitely tilted. Saturn has several moons of interest, but one of the moons of interest, actually, I put up here by name, Titan. Actually, we have landed a spacecraft on Titan, too. And it actually has liquid, it doesn't have liquid water because it's so cold, but it has liquid methane. So it actually rains methane. It's got like a lake of methane. Let's see, Pluto. Oops, okay. So actually Pluto kind of begins, remember a minute ago I said out here we basically have comets. Remember we'll put comets out here? Well, the deal is that Pluto is much more like a comet than it is like Neptune. Okay, so Pluto is basically a rocky, icy body. And if you didn't catch it this summer, some exciting things happened with a spacecraft called New Horizons. I think so, New Horizons. The spacecraft took years in the making and then actually took years to get there. And they didn't have enough energy to insert it in orbit like we have Dawn around Sirius, okay? But New Horizons went right past Pluto and one of Pluto's largest moons, Charon, and got some great pictures. So right now, New Horizons is headed out of the solar system. But it sent a lot of data in, is that July or August? But it sent a lot of data this summer, and even more data is coming, the high-resolution data. So that's pretty exciting. All right. So I said that actually there are generally 2 locations for comets, and those are the last 2 lines there. These 2, I'm going to say comets. Something called the Kuiper Belt. Now, the Kuiper Belt actually is related to something else we already know about. Remember in here when that was the sun, and I walked around with the Earth, and I said that kind of this thing is called the plane of the ecliptic. Remember that? It's kind of that paste paper. All of the planets pretty much orbit the sun on the same plane. The Kuiper Belt, basically the same plane, but basically it's just outside of Neptune, so Kuiper Belt. The Oort cloud, something a little bit different. The Oort cloud is basically with the sun in the center. The Oort cloud is farther than the Kuiper Belt, and again, it's home to comets, and it is spherical, basically with the sun in the center. All right, cool. Well, one of the assignment questions I picked out is basically to tell me how our solar system formed. And I like this. There's a lot of information here, but it says, how did our solar system form? If our solar system consists of everything we just talked about, how did that come about? Well, let's see. The theory that kind of summarizes how it came about is called the condensation theory. I've also heard this called the nebular theory. Must be the same thing. Nebular theory. Now, remember, in here we talked about the scientific method, and theory is not a guess. Okay, theory continues to be revisited, but basically it's all the evidence points to this, and the astrophysicists agree with this in general. So, in the condensation theory, first off, what is condensing? Okay, you might know if you think of water, when water condenses, it goes from being a gas to a liquid. That's condensation. Okay. So when we're talking about this condensation theory, how in the heck did we get our sun and our planets? Basically, we're taking something that actually started out as a gas, coming down to cool down, and gravity kicks in to make our star and the planets. So in astronomy, there's kind of a key thing called a nebula. So nebula, that's an important concept in astronomy. So most of outer space is like nothing, okay? Most of outer space is, if you saw the movie Gravity, kind of creepy, right? But every once in a while you'll run into, and it's almost like a fog, like a chunk of outer space that has gas. Now that gas isn't there for just no reason. That gas is probably put there by a star or something. Okay, but our solar system, which is our sun and our planets, all started out in what we call a solar nebula. So the solar nebula began contracting. Now the way you read this slide is it goes with the figures. Okay, so basically you find one matches up with one on the figure. So right there, that is our solar nebula. It began contracting. The next one, number 2, began spinning or rotating. Okay, and does that make sense? Because you figure, and we haven't talked about the sun actually spins on its axis of rotation too. So the sun is spinning, the planets are spinning on their axes, the planets are orbiting. So we definitely have the spin thing going, and that was originally from this. One of the things about spinning objects is they spin, they will ultimately contract and flatten as they do that spinning. Okay, spin and contract and flatten. So number 3 there, let's find number 3. Okay, so number 3 on the figure, if you compare 2 and 3, do you see actually some little budding planets there? Okay, these are like little budding planets. Kind of if it was a record, you know, that would be kind of like their track, they're kind of clearing their track. Again, when water condenses, what does it do? Water goes from being a gas to being a liquid, something you can sink your teeth into, a liquid, right? So actually that's kind of what's happening here. And I kind of liken it to building a snowball in snow, okay? So they got larger. The proto-sun, so planetismals, by the way, is that not an adorable name? So planetismals are like pre-planets, okay? And proto, like a prototype, means a before. Proto-sun is a pre-sun. Okay, so that's number 3. Number 4, protoplanets clear their orbits. And I can't remember if I'm going to emphasize it much this semester for y'all, but part of a definition of a planet is it needs to have cleared its orbit. And I say that with lament or whatever because Pluto, actually that's the criteria, it fails now. And it was 2006 they finally defined what a planet is. A planet needs to have cleared its orbit. Pluto, let's go back to Pluto. Okay, so we have the sun, we have the terrestrial planets, we have the Jovian planets, the gas giants, and then we have Pluto. The thing about Pluto is if you were to look where Pluto goes as it orbits the sun, there is other stuff in its orbit. Okay, it just wasn't big enough to basically kind of, in this process, gobble up all of its stuff. Basically, Pluto begins what we call the Kuiper belt, which is the comets in the plane of the ecliptic. Okay, so that's kind of where that goes. Okay, so that's number 4. Now, there's a big difference between 4 and 5. The big difference is this, and we'll talk a little bit about this. The sun, lots of energy, right? Okay. The sun finally turns on. It can only turn on when it got hot enough in the center and got enough pressure in the center to begin what we say nuclear fusion. So the difference between 4 and 5 is the 5 the sun turned on. All right. And I'm going to go ahead and mention this because when we talk about the sun, I'll mention it. But one of the cool things, no pun intended, that the sun has going for it is this thing called solar wind. And solar wind is basically like regular wind. Solar wind, my little red squiggles there are solar wind. One of the things about the sun is it goes, when it turned on, it basically has a positive pressure in all directions. So that solar wind basically kind of cleared the rest of the solar system for things that were kind of light and weren't already stuck to a planet. All right. So one of the things when you develop, in science or in life, when you develop a theory, you need to make your theory match with your observations. So this condensation theory is what we say consistent or matches with the fact that all the planets go counterclockwise, okay? Sometimes I go the wrong way. All the planets go counterclockwise around the sun, okay? All but one in particular, maybe even a second one, they all spin counterclockwise, okay? And that's actually conservation of the original energy with the rotation up in step number 2. Okay. Cool. Well, now I get to kind of talk you through a little bit. Most people kind of understand the concept of our solar system, but I want to kind of put you back in time when that wasn't always the case. When I say that, that's to say that most people have an idea that the planets orbit the sun. But there is a competing idea, okay, and let's see. That competing idea is in the first sentence. Instead of the Earth orbiting the sun and all the planets orbiting the sun, they thought that everything orbits the Earth early on. Most people thought that everything orbits the Earth. And, the sun rises in the east and sets in the west, so you might say, well, the sun is orbiting the Earth, right? The stars appear to kind of rise in the east and set in the west. It seems like everything might be, the Earth is. So that actually is what we call geo, meaning Earth. That idea is what we call geocentric model. Okay. So again, kind of back to historically, how do we get to what we know today? And it takes a little while. It makes you wonder where we're going to go with some of the other scientific kind of questions we're chasing down. But the other problem that they had to do with kind of more of an aesthetic thing, not science at all. Just basically said life is not messy. And that's not true. Life is very messy. Basically said that science and everything needs to be perfect, or everything, I shouldn't say, people weren't perfect, but everything to do with nature was perfect. And so if the heavens are perfect, and if kind of this whole idea of the sun and the earth is perfect, the sphere is perfect, is my point. So basically, they thought that not only was the earth in the center and the sun goes around the earth, but said it did it in a circle. It did it in a circle. And that's going to come in a minute, too. So those dots up there, so of course you see the stars. I'll try to see if I can make this a little darker. You see the background stars, right? It kind of looks like the little star thing we looked at with stellarium. And that orange orb is Mars. Okay, that orange orb is Mars. And remember I said that actually Mars and all of the planets, they will appear to move against the background stars. Not in the same night, but night after night. So actually we have clear from June to November the location of Mars. Okay? So usually Mars moves in, this is what we call, usually Mars moves this way against the background stars. We actually call that direct motion. And that actually, direct motion can be explained if you go ahead and have Mars orbit the Earth. You're like, okay, Mars orbits the Earth, direct motion makes sense. Okay. What doesn't make sense is this little loop-de-loo right here, indirect. Okay. And you'll hear astrologists, yeah, I said astrologists, actually call this retrograde. Retrograde. And I still hear that on the news sometimes. And it's not just astrologists, it's astronomers too, but basically it's kind of a backward motion of a planet against the background stars. It's retrograde, or indirect. Okay. So the thing is, the whole putting the Earth in the center when the sun orbits the Earth and the planets orbit the Earth, which is weird to think of, but we can explain direct motion, but we can't explain retrograde motion of the planets. So this guy could, Ptolemy, and the P is silent, so you pronounce his name Ptolemy. He actually said, no, the Earth is in the center of everything and the sun orbits the Earth. And he said, this is how it does it. Okay, notice the Earth is in the center, right? And he picked a planet, looks like he picked Mars or any planet, and he said the planet orbits Earth. This would be a geocentric model. And he said in order to kind of get that retrograde motion, he says every once in a while the planet does a loop-de-loo around a little epicycle. The little gray thing is there, what we call an epicycle. So basically what he said, she said, he basically said that, for instance, this is direct motion. And those little kind of backward motions are right here. So here we have retrograde, okay, and here we would have retrograde, okay, here we have retrograde, okay. So I suppose, but it was very complicated. One of the things of science is the more complicated, I think I might want to talk about hallmarks of science. We said if you make a theory too complicated, you're probably on the wrong track. And he was on the wrong track. So back to the right track. Do you see the title of this? Copernicus proposes sun-centered model. Now, he wasn't the first to think about it. Okay, I think might have been Aristarchus, in the BCs actually said, no, the sun is at the center of the planet's movement. Okay, but he kind of revived it. So Copernicus in 1543 said, nope, it's the sun, and the Earth goes around the sun, and the other planets go around the sun. Okay. So he said that actually we can explain retrograde motion of the planets. Okay, and this is how it works. Let's see, how do I do this? Well, so let's just look at the Earth and Mars and look at retrograde motion of Mars. So here we have the sun, and we have a track for the Earth, and we have a track for Mars. Okay, so Mars is outside of Earth. We are both orbiting the sun, and actually that's kind of what's shown here. Now, here's the deal. When we are near each other, first off, I'll just add this. And actually, Kepler found this out. He's another important name here. But the Earth orbits faster. So Earth equals faster, and Mars is slower. So I think that's important. So actually, you can kind of get a sense for that. Like 1 through 7 there, the blues are marked 1 through 7. It's the same period for the red kind of outside Mars. So you can already get a sense for Earth is orbiting faster. So here's the deal. Let's see, I'm the Earth, okay, and I'm going to kind of redo this figure, right? I'm the Earth, and Mars is here. I'm going faster, okay? But we're both going in the same direction, counterclockwise around the sun. So here, he's over here, or she's over here, and I actually see Mars move backwards against the background, or normal against the background stars. Here I see it move normal against the background stars. The thing is I start to catch up with Mars, and it starts to look like it goes backwards. And then when I go past Mars, it looks normal again. I have likened this to if you are driving down you've got 2 lanes going in your direction, and you are in the faster lane. You're like Earth, okay? And you're approaching somebody that's in the slower lane. They're like Mars, okay? If you look at that car kind of against the background trees or whatever, you'll see that car kind of looks like it's moving this way as you're catching up with it. When you get right up next to it, you'll see it actually looks like it's going this way with you. And then after you pass it, it again looks like it's going the same direction. So kind of, it's a little bit of a strange sensation, I think. But it's a similar thing. So this figure, I think, did a pretty good job of, it said, for instance, when we are here, okay, position 1, Mars looks like it is in the constellation Gemini, background stars. Okay, when we are here, Okay, Mars looks like it's going normal. It's going forward, direct motion. It looks like it's in kind of the edge of Cancer. When we are here, okay, Mars again looks like it's normal. It looks like it's going like it should. It's going in Leo. Now here-ish, 3, 4, and 5, we're basically passing Mars, and it looks like it's going backwards. So the backward motion is right kind of, I'll go ahead and include 3 and 5 there, but the backward motion is as we kind of go past it. That's the best I can explain it. Let's see, did I have a circles there? Okay, yep. Okay, so Copernicus, if you need to know 3 names, these are the 3 names. Copernicus, Tycho, I guess I should say Tycho Brahe. Tycho Brahe is your second name, and this is the order that they happened. Copernicus, Tycho Brahe, and Kepler. I probably have Galileo down here somewhere, but this is kind of the change thinking of back to the sun-centered model of what our solar system is. So I like the concept of Tycho Brahe. So it sounds like he was kind of like a nobleman with cool toys. Doesn't it look like a cool toy up there? Okay. So one of the things about Tycho Brahe, among other things, is he was a great observer and very meticulous notes. Okay, so he studied the planets. He wanted to try to explain that retrograde motion and kind of the motion of the planets in general. But he still could not, you know, you have a solid theory if you can predict where things are going to be. And the problem is they would take their theory and try to anticipate the motion of the planets, and it still wasn't quite right. It was just a little bit off. So after Tycho gave his data, as I understand it, basically to Johann Kepler, and Kepler ran with it. Kepler finally, the big thing about Kepler, and I think it's finally down here, the big thing about Kepler is he finally went from a circle to the planet's orbit in a shape of a circle, the orbit of the sun, into an ellipse. And all an ellipse is basically an oval. An ellipse is an oval. So he said, get off this whole perfect circle thing. That's not the way life is. Life is messier than that. Okay? When the planets orbit the sun, it's in an ellipse. And actually, that's one of his 3 laws. And everything has been downhill since. So Kepler, from the data that he got from Tycho Brahe got his stuff from Copernicus, basically kind of turned the tide, the thinking. So Kepler actually has 3 laws, and they all deal with how planets orbit the sun. So his first law was basically the shape of the orbits. They aren't circular, they're ovals. And an oval is what we call an ellipse. Okay. Now ellipses have, I call them belly buttons. Can you see where those 2 green tacks are? Those 2 green tacks in this, actually those are the foci of the ellipse. So the sun is at one of those green tacks. Okay, so the sun is at one of these foci. And on this figure, the yellow thing is the sun. So can you kind of see where it's lopsided? Kind of the planets orbit the sun in a lopsided sort of deal. Okay, the sun's not right in the center. So sometimes the planets are close. We call that perihelion. Closest approach. Sounds like a NASA thing. Okay, basically the planets are close then. And for us, that happens in January. One of the videos we watched on Wednesday actually said, dude, you are actually closest to the sun in January. And that's exactly what he was talking about. We call that perihelion. Aphelion occurs in July. Okay, and that is the farthest. Okay, so that's one of his 3 laws. This is his second law. This is all Kepler, and this is all about how planets orbit the sun. The second thing about how planets orbit the sun is kind of weird, okay? So basically, I'll go ahead and mark up this thing down here. I'll call this A, I'll call this A, and this B, okay, and this C, and this D. I know it reads kind of weird, but basically, if you were to set your timer, oh, here's another thing. I'm going to say fastest over here at perihelion, fastest, and actually that's kind of the crux of his second law. I can put slowest out here. And it's kind of a gravity thing. Basically, when the planet is at perihelion, okay, it moves fastest in its orbit, okay? And when it's at aphelion, it moves slowest in its orbit. Okay, so what he said is basically if we make these time segments, kind of A to B, one time segment, and C to D, another time segment, if those time segments are the same, basically the area back to the sun is the same. To me, though, and I think I wrote it here, the biggest outcome of Kepler's second law is just what I said. It goes fastest at perihelion and slowest at aphelion. That's it. Okay. His third law, I think, is perhaps the most irritating. Before I show you the little equation that goes with his third law, let me summarize what it says. His third law summarized is the more distant the planet is, the slower its average speed. The more distant the planet is, the slower its average speed. A minute ago, we looked at Earth and Mars, okay? Mars is more distant, it has a slower speed. That's it. Okay? I can't remember how long it takes. Something about Pluto, I know it's not a planet, but actually it hasn't completed one orbit since its discovery. Yeah. Poor Pluto. But the cool thing about Pluto, well, the discoverer, you'd think he would be like disappointed. I think he died before Pluto was demoted. It was Clyde Tannenbaugh, like from the Chicago area, who discovered Pluto back, when Pluto was Pluto. But anyway, they took his ashes and they put him on the New Horizons spacecraft that went out to. Is that not awesome or what? I'm just saying, these people are with it. Okay, so the mathematical part of Kepler's third law looks like this, where actually the P is the period and the A is kind of the distance to the sun. Okay, now I have a slide here. We didn't get to those 3 slides, but I have an assignment slide right here. So I'd like you to do just questions 1, 2, and 3. And question 21 we'll assign after we talk about the sun. I was just too gabby earlier.